Okay, so in this video we're going to look at an example based on the torque speed characteristic again, and this one has less to do with, even in the other example that we've seen, is it's not as mathematically involved. Numerically, it's not very intense. This example is no different. There is one equation that we'll be using, previous relationships that we know to be true. If you don't know where this expression in the pink comes from, I'll link that video in the description below. And the idea of this example or this video is to illustrate a concept, I guess, and to analyze the concept. So what I've done is there is a simulation or set of simulation results, I should say, that accompany this example that have been produced. And I'll include those in this video, and we'll walk through them and we'll analyze everything, and we'll understand how the whole mechanics of everything actually play together to produce a vehicle, I guess, or a vehicle-like profile, because what we're looking for really are these relationships that we know to be true. So we have this question that says to determine the power rating of an induction motor for an all-electric vehicle with the following parameters. Now I'm not going to read the parameters to you, but you can pause the video, note them down if you'd like to try to solve it on your own, or you want to step through it. So take a minute to familiarize yourself with all these parameters, and this expression here again is from a previous video where we derived it, and I will link that video in the description below if you're not familiar with where it comes from. But we can jump right in, and if we want to calculate the maximum power, we can use all these parameters and we can plug them into this expression, and I'm not going to do that in another step, but I will give you the answer of that just so you can check your understanding. And this is 78463 watts. Now, you should be mindful that these speeds should all be in meters per second, and there's a factor of 3.6 to convert meters per second to kilometers an hour. So based on this PT max, you can determine what your force profile should look like. And again, in the constant force region, this will be 78463 divided by 11.1, which is the base speed, and this is true for V less than or equal to 11.1. And then in the constant power region, you'll have 78463 divided by V, and this is for speeds greater than 11.1 and less than 44.4, and this 44.4 is 160 kilometers an hour, because that's what it says Vmax is, right? So there's a Vmax and there's a Vf. So this is your steady state that we want, and this is your maximum speed that the vehicle should be able to operate up to. So these profiles will go on forever, obviously, because this number keeps increasing and this number will asymptotically approach zero. But at some point we'll say we don't want to operate beyond this point anymore, because the vehicle either shouldn't be rated that high. Because there are, I guess, legal speeds at which these vehicles can run. I'm not an expert in policy when it comes to vehicles and vehicle speeds, but I imagine there is some maximum top speed. I guess you can call that your Vmax in this case. So another thing we can model is the resistive force, right? So if you write the sum of all the resistive forces, which are these two here, because you're on a level road, you write an expression that says that Fr is equal to 147 plus 0.338 V squared. So this is your attractive force that you're going to apply. This is your resistive force that your vehicle is going to be subjected to. And now what I want to do is I want to work through a series of, I guess, plots and waveforms. But before I do that, I want to tabulate some results. So let's call this the balance of Fp dV by dt and V, right? So the balance of force, power, acceleration, and speed. So what do we have? We're going to tabulate some results. So you'll have V, this is in meters per second. You'll have your attractive force, this is in newtons. You'll have your resistive force, also in newtons. You'll have your attractive power in kilowatts. Well, I guess let's use watts since we've used watts so far in this example. And then you'll have your resistive power, also in watts. and then you'll have your acceleration dv by dt in meters per second squared, of course. So the speeds that I'm interested in, which ones am I interested in? I'm interested in 11.1, because that's our base speed. I'm interested in 27.8. I'm interested in 44.4. And then I'm interested in this fictitious speed that I'm going to call VSS. For now, it's fictitious. We'll define it in a second. So using the expressions that we have above, that's how I'm calculating these numbers. I'm calculating these numbers so that we have some rough metric as to follow, I guess. So when we look at our results, we won't be, just walking around in the dark wondering what it is that we're doing. We'll have some guidelines to follow. And so these are the results of the expressions that we have above when you evaluate them at certain speeds under certain conditions, and the conditions or whatever these are stated here. These are 784.63, and this is true all the way because this tractive power is constant after the base speed, right? So if it was less than that, then you would have a different expression there. Here, the resistive power does not stay the same since the resistive force changes, but that's not an issue because we can calculate all of these using the resistive force expression along with the speed, and the speed is the ones that we the ones that are listed here, I guess, on the left side in the first column. So here acceleration is 4.59. Here this is 1.62, here this is 0.64, and here this is 0. So you'll notice I haven't yet defined what VSS is, but I know that at some point I will reach what is the steady state of the vehicle or the motor, and at that point the acceleration is 0. And another thing you'll notice is that the tractive force is equal to the resistive force. The tractive power is equal to the resistive power. So this is a steady state condition. Now, when does this speed occur? Because this speed may occur before, it might occur before, but based on the trend that we're seeing, it doesn't occur before our maximum speed. Because we see that this force is less than this one, meaning, and since we know that force is inversely proportional with the speed, we know that this speed must be higher than this speed. Well, we know that VSS must be larger than that. So how do we calculate VSS? Let's look at steady state speeds. Let's say VSS. How do we calculate that? It's a straightforward calculation. So we say V equals VSS dV by dt equals 0, steady state, no acceleration, meaning the resistive force equals the tractive force. And you can use the expression that we had up above for the resistive force. And this will be VSS, lowercase v. Every now and again I forget that we're using lowercase v's for these things. VSS squared is 78463 divided by VSS. If you solve this, you'll get that VSS is equal to 59.1 meters per second, which is equal to 212.7 kilometers an hour. Now this is very clearly larger than our maximum speed. So I mean, we're never going to reach this if our vehicle operates as intended, but this is the speed that it would settle at if the tractive power was kept constant at 78.4 kilowatts roughly. So the vehicle would speed up to this speed. We're not going to let that happen, but it would, right? So at that point, we would expect then the tractive power, the tractive force, and the resistive forces to become equal. Now, if we look at, this is where I guess we can start to look at simulation results. And so here are some simulation results for the vehicle that is discussed in this question, right? So what's what? I guess we can use some color here. Let's use a blue. And you'll see here, first of all, that this is the constant force region up to here, right? This point here, it shows you, well, that's where the base speed is reached, right? And another thing to be mindful of is that this plot is time here. This is time. This is not speed, right? Although the profile looks the same or similar, It's not speed, this is time. So you know that this is a constant force, so you know this is the constant force region. Now if you go down, I guess, and you just kind of roughly follow it to this plot, you'll see that 40, or this region, and we'll zoom in on this later, lines up with that constant force. I mean, my line was a little off. In any case, you'll also see that if you keep increasing, or if you just let it run as it is, the tractive force just goes, and that means the power is kept constant. So if the tractive force is still going as it does, the resistive force becomes equal and the power would remain constant. And you also see that this speed, this is that 212.7 kilometers an hour that we have over here. So this shouldn't be allowed to happen though, because we said our Vmax is 160 kilometers an hour, right? Which is 44.4 meters per second. So if we want to zoom in to this plot, let's zoom into this plot. So I have the zoomed version of this plot here. And this, I mean, is more, this one has more emphasis on the constant force region, right? So if we look at the constant force region, we would see here that this region here, well, I mean, my line is pretty bad and I probably should use the line tool, but that one glitches sometimes. So in any case, up to 40, we know 40 is our base speed, so maybe we can get rid of this so it doesn't cause confusion. We know 40 is the base speed, and we see that this is a very linear increase in speed from 0 to 40, which is what we expect. And this is constant from that during that time. Then the force starts to drop off, and the speed starts to increase at a non-linear rate. Another thing we should look at is the acceleration time, right? So we want 0 to 100 to be roughly 10 seconds, and this one just, I mean, it meets that to about 9.2 seconds, I think it was, when I checked the simulation. 9.25, 9.3, something like that. But this is very close, and it meets the 10-second requirement that we had. And something we should be mindful of is that the steady state speed, as we showed here, and we showed with this calculation, is greater than the maximum speed that we want to allow the vehicle to operate at. What that means is once our vehicle reaches our maximum speed, we should decrease our tractive force. So what's our maximum speed? Our maximum speed is, we said 160, right? So 160 happens, let's say roughly here at 25 seconds. So this is once we've reached our maximum speed of 160, we would like to decrease, well, that's a bad color to use. We would like to decrease such that this becomes equal. And if the two become equal, then we would be cruising, or we would stop accelerating, or our speed would be constant at 160. So now if we go down and we insert our next or set of results, I guess, we do exactly that in the simulation, and you see that we have the same behavior. So from 0 to 40, whatever the time, that 2, I think did we calculate that time? No, that wasn't this example, that was a different example I'm thinking about. So until this time, or we could calculate that if we wanted to, really, just by integrating. During this time, it's a linear increase, force is constant. Force starts to decrease, speed starts to increase non-linearly. Then we realize that around 25, we've hit 160, and then you'll see all of a sudden the tractive force drops to be equal to the resistive force. And since the speed becomes constant, the resistive force becomes constant, and the tractive force is constant because we're forcing it to be that value. And we're at a speed of 160 and we're constant there. So now what you need to think about is, how do we do this? Now, when we drive, we do this by easing up on the gas. So we stop pressing the accelerator so much. And we observe that the speedometer says 160. Usually doesn't say 160, it usually says something like 100. But let's say you're allowed to go up to 160. We're not in Canada, anywhere that I know of at least. But let's say you go up to 160 and you say, okay, I want to go to 160, and you press the accelerator just enough to be at 160. You've basically given the command to the machine or to the vehicle, which will translate that through whatever means. I mean, we'll see a bunch of different methods as to how you can control the force and the torque and the speed of the vehicle. But basically you give a command and say, okay, look, I'm fast enough now. I need to stop getting faster, and I want you to stay just this fast. And so you decrease the force, and then you stay constant there, and you see that this is a constant speed. Now, alternatively, what you can do is you can do another thing. But what else can we do? We can say, what if we want to go backwards, right? Let's take a look at if we want to go backwards. So if we want to go backwards, so this is the previous case that we just discussed. So you do this, all of this, and then you cruise for a bit, and then you decide, hey, I want to go backwards. I want to reverse, and I want to slow down. Well, I don't want to go backwards. I could go backwards, but I'm not going to go back. I want to slow down. That's my mistake. I didn't mean to say go backwards. But you could go backwards, and we'll discuss how that happens. So standard stuff from 0 all the way up to 25. We've seen this already. To 35, you cruise until 35. Then at 35, you're like, okay, you know what? This is too fast for me. I want to slow down. Or, you know what? I'm getting off of the highway. I need to slow down because I can't be going this fast on small streets. Because some people do. I don't know. In any case, I don't recommend you driving at 160 kilometers an hour unless it's legal. If it's legal, go for it. If it's not, please don't. So you would decrease the force here to decelerate the vehicle, and you'll notice that once you get back to 40, and this force starts to go constant again, this decrease becomes linear as it was increasing here, which is what we expect. Now the part about going backwards that I was saying is here. So once you reach 0, you bring the force back up to 0. If your force remains negative here, your vehicle will begin to reverse, which is scary, because if you want to slow down and all of a sudden you start going backwards, people behind you are probably going to hit you, and you'll be in a messy situation, I guess, to say the least. But you have to be mindful of all these things. You have to be mindful of when the force goes to 0, what a negative force implies, because it's not enough to just say that we go to 0 and we stay at 0. So you have to force it to stay at 0 by decreasing the force. Right. So during this time, I mean, of course, the tractive power would be reversed as well, since the tractive force is reversed and the speed is positive. So the product of those two would give you a negative power that would decrease. That starts to happen here, basically. So you have a negative power during this time. And we'll see, I mean, in later videos that this energy, that you can actually recover this energy, because this is a negative power. So it's basically power coming back to your, it could be power coming back to your energy source. Which is referred to as regenerative braking. So we see all of this type of behavior here, I guess. So one thing to understand is that if we have this upper limit, if we change the upper limit of the speed, right? So the upper limit of the speed was 160, but the maximum PT, so let's go back to the top for a second. This equation assumes that the steady state speed carries on and continues. Now, if we want to limit that, because we have the limit on the top speed, we limit the maximum power we can have. So then the amount of power that you need for that would actually end up decreasing. So the tractive power in these cases, 160 times whatever these numbers are, would give you a smaller value than the 212 that you need. So the point I'm trying to make there is that there's a difference between the, I guess you can call it like a natural steady state speed, because the vehicle would keep increasing to there, versus the limited one, right? So the limited one would mean that we need less, we require less power to actually achieve that. In any case, that's just a side note on what we've seen so far. So why don't we wrap this up now? Because this was a fairly lengthy, I guess, discussion about things. So what did we do? We didn't do a whole lot. We used this expression to determine this maximum power. We determined this profile. We determined the resistive force. We calculated some different values. And if you look at these plots, you can actually confirm that these values exist at these different speeds. So I mean, at 11.1, which is here, this is 7,069, which is roughly what you see there. Resistive force, you can calculate, I mean, all these things. So you can confirm that these profiles exist based on these numbers, which is why I've provided them for you. And so yeah, we went through some different scenarios here, and we saw how the vehicle operates under different conditions. We saw how we can limit the speed to stay at the maximum that we need, and wrapped it up with a, I guess, from 0 to cruising back down to 0 situation. So I hope this was helpful. Remember to like and subscribe to support the channel. If you have any questions, leave them in the comments below, and we'll see you in the next one.